computers, but first I wanted to just to briefly review a bit what we did yesterday with the Fourier transform pairs and everything. So when you open the software, you can immediately realize, and if perhaps somebody missed yesterday a bit. Yeah, so this is the idea that I gave you, that when we have two antennas, we are using a geometric delay to take that signal, those voltages in the two antennas into the interferometer. So this is a slide that I found that perhaps is with more maths, that perhaps you like more, where you can, here you have the two lines where the wave comes to us, two straight lines. And if we assume that we have two antennas pointing there, you see that there is a delay just in the second antenna, just because the wave comes from there, right? So if it's just like, this would be like the delay for that antenna. And so if you have a wave here that arrives at time 0, let's say at this antenna, then you will have a delay on the other antenna. So then you correlate those two measurements. You send them to the correlator, and then you make an average in time. And this is because this is rapidly varying. This will, at the end, it will be averaged out. So you end up having information on the original wave that came, right? So we are basically willing to recover how the wave is. So if you need more details on the math that goes behind, just let me know, and then I can point you to the right chapter in the tools of radio astronomy or in the different presentations.
Sorry,
yeah, tell me.
These are subs. Is exactly what?
Yeah, this is the correlation of the two signal of the two antennas. We are just measuring voltages, and we want to recover the intensity at the source. So.
Make them in phase.
Sorry?
All signals.
So it's the same wave. The wave comes from the sky. The planar wave comes from the sky, and then both antennas are receiving the same wave, but with a delay. And then, this is what we are using for measuring, for recovering the information. This is a schema of what goes into the correlator, because I told you yesterday the correlator is a supercomputer that makes quick calculations every second among all the baselines that we have. So this is just like the previous slide. So we measure waves. By convenience, we move them to a lower frequency to make operations. They are quantized. So we can only make measurements in 8-bit mode, or we just have to put it in a bit mode for the computer to make the calculations. So then we do the cross correlation, and then we get the visibilities. This is what we will be working with, visibilities. Again, just to remind you that, so this is our source plane, our image plane. This is what we want to recover, and this is what we are measuring. We are measuring visibilities in between baselines. And this is the Fourier transform of the original image. Okay, and this is to answer the question that yesterday arose, that why in the UV plane we show minus and pluses points. When we remember that when we were discussing, there was a question why, if we just have one baseline, why do we have 2 points in the UV diagram? So because the signal is real, as perhaps was Nicolas that mentioned. Then we have that the negative is the conjugate, so we get 2 visibilities for just one measurement, and that's why we plot those 2 points in the UV plane. Okay, and this is just a quick review of different Fourier transform planes. So a delta function will give you like a constant amplitude on the other side. A Gaussian, a narrow Gaussian gives you a broad Gaussian on the other side. And yes, just to review what we did yesterday. And then also that the faces give you information on where are the sources located with respect to the center of faces. You will be playing with this in the software that we will be using. Okay, I also mentioned that, this is another way to show how a point source look like in the UV plane, because it's a point source. It has a constant amplitude and 0 phases. And these kind of sources are the ones that we use to calibrate the array. So we know there is a strong source in the sky that looks like a point source, and we know it should have a brightness, a flux of 3 Jansky. So then we set the array to have such a response. Okay, so yeah, this is just an example. Here you have the UV distance, the baseline distance in this axis, and flux in the other one. Okay, this is the source that is responsible for this signal in the UV plane, in the visibilities. In the case that you had a source with has much more structure, is not a point source, you could have things like that. So it's not a point source anymore. You don't have constant amplitude and 0 phases. So you will see these kind of things when you work with your data. And this will correspond. Sorry, I don't have the image. I will look for the image of this target so you can identify it. And for instance, this would be a planet. This is how a planet would look like in the visibility space. So you have the amplitudes here with some ripples, and then the phases that go like this. And that would correspond to an image like that. So this is the planet in the image plane, and this is the planet in the visibility plane. Okay? Yeah.
Why? Like, why do we get in the visibility plane? Why do we get that?
This one?
Yeah. Like, what does that mean?
That means that you have like a kind of a Gaussian, right? The Fourier transform of a Gaussian is another Gaussian, but with different width. So you have like a first Gaussian, and then some residuals here, and then the phases that are there. Like, it tells you that the source is kind of circular. It has a circular symmetry.
So that this is only the right side of the Gaussian.
These are the phases, and this is the amplitude. So when you have in the visibility plane, you work with 2 magnitudes, so with amplitude and phase of the wave. And this is to go back to something like this. Yeah, that could be like a sharp disk. This would be like the transform. So. Yeah, I just look for some examples, and this will be like a much more complicated source. You can see, like, this is not very intuitive to actually see what is the source that is originating such a pattern in the visibilities. But this is the original source. Okay, so this is the image, and then in the visibilities you will get something like that. So from that information, we want to retrieve how does the source look like, okay? So to get used to how this works, there are 2 softwares that are available. Well, there are more, of course, but I found these 2 that look quite okay. We will be using the first one, but this one here is also suitable for learning how an interferometer works and how to make images. Yesterday we installed these apps in SIM, in the computers here, I think they have been copied in their home directory. And they are compressed, right? So, but I think in the Ubuntu you can just double click and it will be in home. In home you should have like a tar file like this.
Casa release.
Ah, pero este ocupa poco. Okay. So there is no apps in SIM. Okay. Sí. Sí. You can perhaps look Google this. How do you say? If you put in Google Nordic tools, Alma, because there is a node in Sweden which supports Alma, and there are some experts there. And in particular, Ivan, one of the experts that works there, he developed this software, and he has a lot of tools for Alma in this website. I can just go and do the same. And then you go here. Sorry that it's not installed. That we thought that. Yeah. So you go to apps in SIM, and you download this source code. En este sí, en el mío. Pero yo estoy con mi laptop. Y en el número 2 sí que se descargó. Bueno, whatever. Ah, sorry, yeah. Nordic Alma tools. If you search for Nordic Alma tools, did you get it already? Okay, so then we'll have to look into, because if we need to copy the Alma data to all the computers, then we can take a look to that later.
Software tools.
Or perhaps I can put it. Or if I think in Ubuntu you just double click on the compressed file and it opens a folder. Of course. Sorry. You are a terminal man. Is everybody has already uncompressed the
Source code.
the ones that you have the software there already, you can just open it by doing Python. Well, you can go to the folder scripts and then do Python appsinsim.py, and it should open a nice window. Do you guys have it? In the folder, in this one, you have a PDF, which is called instructions exercises.pdf, and that's the guide that Ivan made with explanation on how the software works. it's there. In case you are super advanced and you want already, have you opened already the GUI?
Okay. Okay.
And the teacher, how is the teacher doing? Okay. So you open a terminal and or you open with Python. See? Mm-hmm. Okay. App sim. Is anybody having trouble to?
Okay. Arrays.
And then you go to scripts. Scripts, and then you do Python appsimsim.py. Oh. I should take a.
We're going to run this Python directly.
Yeah, appsimsim. Yes, it should work. At least we tried in. I tried yesterday in one of your computers and. Hey, beautiful, isn't it? Yeah. Okay. In the folder that you just uncompressed, you have the PDF, which is called instructions exercises, which is with all the explanation on what all these windows mean and if you can, how you can.
Source models? Or
No, this.
instruction exercise.
Yes. And how to zoom in and out with the Z or something.
We already have the program working.
Yes, I think they. Yeah.
Python code is running. Okay. Somebody have problems?
I think everybody's okay. You were the last one.
They're smart.
Okay, once the teacher has everything working, we move on. Okay, so all of you should have this beautiful GUI in your screens. So here you have the array, the antennas of the array. It's very natural because you can. Sorry.
That's weird. That's happening right now in Alpha. That's the
No. This is an example, an array example. No. This is not Alma. It's just you will. It's a fake array. It's an imaginary array in your computer. So, yeah, each one of these dots is an antenna, and with the mouse you can just grab them and move them around to see what happens.
Oh, great.
Okay, and well, yeah, you have. Of course, this is the source model. So there is a source model. In this case, this is a super extended source, very nice, very beautiful. Perhaps it's not the best one for starting. We will work first with a point source and then move on and make more complicated things. Up there you have where the array is located on Earth, because also the latitude and where is the array located, it's important for which sources you will be able to observe. Okay? This is the famous dirty beam point spread function that I was trying to explain yesterday. So this is the response of the array to a point source. This will tell us which is our resolution, right? And okay, this is the source model, and this is the dirty image that you get by observing this source model with this array in these conditions. Are you all following? So you can play. So if you don't touch anything at all, you just leave everything as it is. Here you can choose the observing time, at which wavelength you want to observe. It's also important that you try to move this wavelength because you will see that the resolution changes, right? The robust, we will talk about that later because this is related to the imaging procedure, and we haven't talked about that yet. And then here, finally, you have some, you can choose to add antennas or remove antennas of the array. The reduced data, we will use it later for imaging. So for the moment, don't play with that. And then, yeah, if you make like a super strange array that you would like to save, I think this allows you to save it in your computer. And here you can choose, by selecting load array, you can choose different arrays that are in the different arrays that you can play with. There is a VLA array, there is the ALMA array, there are many other arrays there. And finally, load model to choose which model, which source do you want to try to observe with such an array. Okay, so yeah.
Those model images are real, or it's the same as
You will see. They are based on real sources, yes. But it's a text file that you can edit at your convenience. So you will see in your folder, if you go to your folder, where is it, sorry?
arrays, source models.
Yes, in source models, you have,
Great.
actually it's one of the exercises that you have all these source models that are basically text files. And if you edit one of them, in the header it explains how does it work, how you can modify that source model to move it around or to make it broader or to add components. So this will be something that you can play with. In arrays, you have all different array configurations, the VLA more compact, and Westerbork array, the one that we have in the Netherlands.
This, in fact, is the Nebula model. So
Yeah.
let me see this.
Yeah, so I would say we are here. You can play with. I would say that we all.
Great.
Okay, sorry. Oh.
All right.
I would say that we all try to play with it to kind of together, or if you are super advanced, just go ahead and make your own array. But I would first like you guys to put to load a point source model here, just the point source. Yeah. We can do that.
Okay. Where's my point? Yeah. Acá puedes cambiar el modelo. Y acá puedes cambiar el arreglo del load model. ¿Ves? Ya queda al modo on source. Okay. Ahí. ¿Ves? Cambia todo.
Okay. You can play with this gamma, I think.
And which
change.
way?
The point source, it's here,
Yeah.
and it's not centered.
And which is this array configuration? Do you remember from the
It's
from the arrays? Will they? Which one did you go?
no, it just the model. Yeah,
Okay.
I use the point source model.
This one, the original, is for
The-
the load for the array is Golay 12.
The Collet 12. Okay.
Yeah. Okay.
Yeah. Okay. So here you can play like changing the wavelength that you are going to observe. Okay. You can also play with the observing time,
Okay.
and then you can see here for how long are you observing the source and how the UV plane gets populated. And then, of course, you can also change the latitude and declination of the source. And you can see that there is an effect on the UV plane, a clear effect on the UV plane if we observe like depending on where is our array located, we have a different UV plane. It's not so circular anymore, right? Because it's perhaps a low declination. And this will have an effect on the resolution that we can achieve as well, and for how long do we need to observe sources that are not at the best projection possible. Okay. Yes.
How do you think, how the people of ALMA know the antenna distribution?
Yeah, it's
How can you think an array distribution?
this is
for
one of
coverage?
this is one of your exercises. Yeah, it's so if you want a high image fidelity, what you want is a distribution of the antennas that covers as much as possible this UV plane. So this kind of configuration of spiral way gives you a good coverage as the Earth rotates. So let's do this now. For instance, you can go and load the BLA array. For instance, we can do open, right? If you, the load array, we will use the BLA C, for instance, BLA C array. So then you have a totally different UV pattern, right? Because the BLA is a Y shape. So if you observe for a very short time, you will just get the Y. And then the Y starts rotating. So you get this kind of UV coverage. And this is also telling you, because you are sampling the UV plane this way, you have an impact in your image. So if you think of more smoothly spread array in a kind of a circular way, which antennas that are well distributed, then you can recover much better all the information.
Is there any mathematical model?
Yeah.
in order to
Yeah.
the UV coverage?
Like you mean like if they did a model and they fitted like an optimum of for something? I guess they did.
To cover all the UV plane,
Yeah, I guess they did. I'm sure they did because they probably made something like that and model at the ALMA site for different time durations of observations. Because the typical observing time of ALMA, if it has to be around half an hour, and then you want to observe certain sources and achieve whatever sensitivity you want, then you break the observation into small pieces, and then you combine them all. So I'm sure they did probably a lot of work to decide how the array should look like. And also, very importantly for ALMA is the short spacings. So this is related to his question that for ALMA they added an array that tries to cover the short spacings as well, because this is an important piece of information that you may lose if you use a very open array that has no short baselines. Okay, so I thought of following a bit of Ivan's suggestions. Oh, yeah, just take your time and play a bit with different models and arrays and observing time, rotating the Earth, or I know you guys are very fast, so yeah.
Carmen,
Tell me.
what means Lena mode?
I don't know, to be honest.
Ah,
Yeah. So actually, the funny thing of the other software that I mentioned that finally we didn't use because this one has the extra helping feature of learning how to reduce the data. The other one is just to play with the images. So Pinterferometer, the other one, you can use your webcam to take pictures of yourself and then make them go through an interferometer. And I think this is quite cool. So yeah, I don't know, because it needs some libraries. Perhaps in these machines they would require an extra installation of something, I don't know. But if you are, yeah, you can try, and there is no webcam here, right? In those. But in your laptops or whatever you have at home, you can play with that. Or we can take a picture of us later and put it through our terminal.
Would you please load the VLA array again?
Yes?
So I can ask a question. I don't really understand why that pattern gets formed in the UV plane. Like,
Oh, you mean this?
yes.
So I guess if we just I think, yeah, really. So this would be like for a very short, perhaps I can retrieve again. Remember that in the UV plane we are having the positive and negative. So you have the Y shape, positive and negative. So that's why you have this kind of star.
But that's a pattern that gets formed when the array starts
To
rotating,
rotate.
right?
Yeah.
I just don't see it. I just don't see how that pattern gets formed.
By
while the array
well, you can.
like what would be the shape after the array rotates?
You
around
can.
zero?
You can start taking out antennas, for instance, and see what happens in the UV plane. Or you can load just an east-west array to see what is the pattern that you. Let's say that you just have one of the, right? One of the wings of the Y shape. So the UV will be just a straight line. You can play taking out antennas,
Yes, yes.
minus, minus, minus. And then if you start adding antennas again, you then see, because every point is the distance of every baseline with respect to all the others. So you are having,
Why is it that when we add this 17th antenna,
That's
there's like a new line here of points? That's what we don't get. Like, we're gonna subtract that antenna, then we add it.
but then
This-
these are,
this one. I don't understand why.
so probably the long ones must be this, like from 17 to all these pairs here, and then this one to respect to this, to respect to this, to respect to this. Because that must be a short.
So when we add that 18th antenna, the points that are appearing here are what? Chun chun chun. No, I just don't see it.
Okay, so let's take out until we only have one.
There?
Take out the 10.
Yeah.
Okay. So this tells you or-
Isn't this shape that gets formed after the array rotates around itself?
No, this is not rotating yet. You are not observing any time. This is when the Earth rotates, then you get this. Ah.
So
So
that's
this is
what's-
the
what-
observing time, okay? Here you are just observing during this time when the Earth rotates. And if you just put them, the starting and the ending time at the same, you are not rotating anything. If it's this exactly 0, then you just get a single point. But it's very difficult to make this exactly.
So why is so okay? So the Earth is not rotating.
Now it's so
There's
you
no
have
time
to see-
passing between
Yeah,
observations.
yeah. That's why you have this kind of fluffy points. But we mentioned yesterday that we have the symmetric, so
Yeah, yeah.
perhaps we can just think
Now we get that
on one side. So you just have
like two
the,
branches.
yes. So the distance of this with respect to this with respect to this, and this,
Yes.
right? So with
So
every
with-
pair, and because they are very close, you have baseline distance. This with respect to this, to this, to this.
So when we start adding antennas,
You have a baseline distance of a short one, a larger, a larger, a larger, a larger, and the largest. And then you have this antenna with all these ones plus, sorry, this one with the other
the
one.
10th one with all of them.
All of them.
But shouldn't we see lines instead of points? Why do we see points?
No,
Why?
the point is the baseline.
So the baseline is not a line, it's a point.
It's a point, yeah. I know. It's because it's a measure of the distance. It's a measure of the distance of the baseline. It's a measure. So for, yeah, you see a
So
line here,
every
but
time-
this line has a value of 10 kilometers. So it's in 10, the unit 10.
And minus 10 because of the...
To the other side, yeah.
I think I'm getting it.
Yeah, no, it's tricky, and once I'm telling you because once you get used to, you first think about it for a while, and then you kind of assimilate it, and then you forget, and you assume this is natural, and then of course because when it rotates, it makes like these things, right? But it takes a while.
Okay, thank you.
Okay, I hope, yeah. There is first one other person, sorry. Yeah, he was first. Tell me.
Es que no terminamos de entender cuál es el significado de H0
Ah,
y H1. Well, what's the meaning of?
What's the meaning? What's the meaning of? Yeah, many people have it, so I will explain it there later. This is the starting observing time and the ending observing time
But,
in the hour angle. So you have the Earth in that right corner. So if the hour angles, both of them are the same, you are observing just a shot, a small, but if exactly the same, it's very difficult to make the bars 0, right? So at the same point. But this is good if when the two bars are equal, this is just a second, a moment. You can think of, here you are just observing for a second. And then when you move the ending time, then you rotate the Earth. So if you want to see the imprint of the array in an instant, you put these two bars at the same. You can grab it and try and move it, and then you will see that rotates. Tell me. Oh, con el VLA, que además esta originalmente se observó con el VLA, esta fuente. Sí, dime.
Estas dos cosas, pues cuando yo estoy moviendo la latitud y la desconexión, ¿qué es lo que estoy haciendo? Porque
Claro, VLA es un array. It's an array that is located in New Mexico. So then you have like a part of the sky that you can observe with optimal conditions, and then there is a part of the sky, the southern hemisphere, that you cannot observe. Okay, so when the source has a very low declination with respect to your array, then the projected baselines change. So if the source is totally at the zenith of your array or at high elevation, and then your array rotates, you can get of a kind of a circular pattern UV plane, right? But if the source is not in a high declination for your array, then your projected baselines move like this. So this gets like compressed in one direction. So then you need, so your beam it's distorted to a certain direction, and there is a point that you have no resolution, because you end up as if you had a line of that's the idea. So you just have a line. In the extreme case, you just have a line, and then as long as you move with observing higher declination objects, then you have more circular shape, and so your resolution will be affected by that, and also the observing time that you need to cover the plane. So you can, if you try to put lower declinations, you will see how the array goes, and then you will see the beam and how the source looks like. And that's why ALMA, for instance, has a limit in the sources that they can observe of plus 40 degrees in declination. So higher than that, ALMA is in Chile. Higher than that, you cannot observe. Okay. So try and play with, very good. Good job. Carmencita.
Carmecha.
Carmenche.
This latitude and declination values are for the array or for the object? Or
No, these are for the object.
okay.
And this, so yeah, this is for the object.
But this
You will
when
see,
you
see.
When you change. Oh, okay.
Yeah, so for instance,
This is the sky sphere or something?
this is the Earth.
Ah, okay.
And this is your array, where it's the array, where is it located?
Ah, okay.
So
Sí,
it's-
es donde está la red sobre la superficie de la Tierra. Entonces, claro,
Yes.
la posición del objeto cambia.
Yeah, so, okay, this is related to,
O sea, nos vamos a quitar
you will have some, we can do it, Alma, open.
You can change the values manually.
I'm not sure, perhaps. I mean, I'm sure there is a way to do it, but what do you mean, like the declination or?
But latitude is, but the declination is. Okay.
So I think even I think the code is clever enough, guys. So many people have this question regarding what happens with the declination of the source. So so your array on where is it located in the Earth is there, and then here you can play with the declination. And this is important, of course, because if you are in the southern hemisphere, you can have access to a certain part of the sky, and not to the So there are sources that you cannot observe, but here you see the limits of your array. So if you, for instance, it said in the ALMA proposal guide that the limit for ALMA is 40 degrees in declination. So sources that are at higher declinations, they cannot reach that. And why is that? So if you have such a case, so I think here Ivan has plotted the limit of perhaps of the array. Here it's 40, so I guess. And here you can see what is the effect in the UV plane of having such a source, right? Because now your projected baselines are not, so yeah, your waves are not so nice, not so straight. And now you have projected baselines that are, you are losing resolution in one direction. So yeah, this is I guess to answer the question, why is this important? So here you can put the VLA, which is in New Mexico, and then you can see which sources you will be able to observe and which ones not. Okay, so, oh, sorry. Okay, so I thought about some exercises that you can just do, and then you can send me the results. It's very easy. With just a screenshot of what you have done, to see that you have been playing with the software to simulate that case, that scenario, that should be okay. So because we promised with Alan to give some goodies to the ones that do the best, do the exercises. So, okay, so for instance, this is a case of take the point source model and 2 antennas and look just with 2 antennas and a point source and discuss what is the dirty beam and the dirty image. Okay, play with the wavelengths that you are willing to observe, and then so just follow kind of this example if you want. You can make variations. If you don't want to do this exercise with a point source, you can do it with something else. So just to show me that you have played with the wavelength, with the different arrays, and then here I had the idea. If you want, you can go to the source models, and you can edit the point source model, because now this place is not in the center of phases, so you can modify it to put it at the center. So you can see what is the effect in the phases when you move the source from the center. Okay. So you can make a snapshot of that and send it to me. Yeah.
So
That would be an exercise.
This is right now,
What time is it?
it's 10:24. So maybe,
I don't know. Yeah. Do you want a break?
yes,
Do you want a break?
yeah.
Okay, I will give you these notes anyway. So I will put them, perhaps I will try to put them now already in the website. So you have them there already. We can have a break if you want.